All right, welcome back. This is the mathematics of data models for lecture 11. Today, we're going to talk about singular value decomposition. So, this is a Northeastern University course called CS 2810, and I am Professor Wu. So let's get started. So we're going to start today with some properties we haven't gone through yet, specifically properties with transpose. Okay, so we learned previously the meaning of transpose. Basically, if you have matrix A, and if you're trying to transpose this matrix, you add a T here, and you essentially flip it so that all the rows becomes columns, right? All the rows becomes columns. Right? So when you do transpose of one matrix, it's pretty clear what we're supposed to do. However, what happens when you have multiple matrices, right? And let's say you have these two, they're adding together, and you're taking the transpose of their result. Or this one, where you're multiplying two matrices together, and you're taking the transpose of the final result. What if they are transposes that you're taking transpose of, right? Or you have multiple matrix transpose together. What happens then? Well, is there a special relationship that governs the transpose for multiple matrices in parentheses? Well, yes. Yes. With multiplication, you can flip all the symbols from left to right. So, and then you put the transpose. So if you have A and B, you flip A and B, which is B and A, and then you put a transpose on each one of them. Similarly, even if you have more multiplications, BCD here, you're going to flip it to a DCB, and then you put a transpose on each one of them. So D becomes D transpose, C becomes C transpose, B will be B transpose. So if you have two transpose, that cancels each other out. With addition, right, there's nothing to flip, right? You don't need to flip nothing. You just put transpose here and transpose here, and that's it. So addition, the transpose move directly. Now, with determinants, right? When you take a determinant, the transpose of a determinant is actually just itself. So transposing it, the matrix, doesn't really matter. And if you have the transpose, and you have a transpose of an inverse, well, that's equivalent to the inverse of a transpose. Okay? So wait, this is the inverse of transpose is equivalent to the transpose of the inverse. And lastly, the transpose of a single value, like 3, is just itself, right? Or if you're doing the transpose of A times 3, then 3 stays by itself and A gets transposed. So these are all the transpose properties. What happens when you do them? When simultaneous matrices are multiplied together. Okay, inverse properties. So with inverse properties, well, property 1, if BA, right, returns an identity matrix, then this implies that B must be the inverse of A. So that's what that property 1. Property 2, when you have inverse for multiple matrices, it acts just like transpose. So ABC is going to become CBA. So you flip every one of them, and then you take the inverse for every one of them. Okay? So ABC becomes C inverse, B inverse, A inverse. Now, inverse of an inverse is just itself. So it acts very similarly to transpose because the transpose of transpose is also itself. I showed you this previously. The transpose of the inverse is the same as the inverse of the transpose. Now, inverse of a number times A. So if we have number alpha times the matrix A, and we take the inverse of that, well, what happens? A gets inverted, right? And capital A is alpha gets inverted, and capital A also gets inverted. The inverse of a 2 by 2 matrix, we have gone through this previously, is essentially 1 divided by the determinant of A, and then you flip these two. So AD becomes DA, and then you put the negative on this. So the determinant of A, if you remember, is AD minus BC. Okay. So that's the inverse property. Now, diagonal matrix properties. So a diagonal matrix, you may remember, is a matrix that is all zeros except the diagonal elements. Okay? This is another one. Now, a special case of a diagonal matrix is called identity. In this case, everything is zeros except the diagonal, and the diagonal must all be ones. Then that would be an identity matrix. For a diagonal matrix, it's really easy to take the power of the matrix, right? So if you have square of two matrix, that's equal to the matrix multiplied by itself. And when you do that, that is equivalent to 1 9. And if you pay attention, and you will realize that this is just equal to 1 square, 3 square. So this square is equivalent to squaring the diagonal. Now, this doesn't work if you have just any generic A transpose. You can't just take each element and square it. It's only for um, a diagonal matrix. Now, this is for power of 2, right? But if you have higher power, like power of 4, where you have to multiply 4 times, you can try multiplying it, but your final result is going to be this. So essentially, whatever power you have here, you can just take the power directly on the diagonal elements. And this even extends to inverse. If you want to take the inverse of this, it's as easy as you just taking the inverse of everything on the diagonal. And if you don't believe me, you're welcome to multiply it out. Like when you multiply by its inverse, you're supposed to get the identity. And here, you would get the identity. Now, these properties are only for diagonal matrix, okay? Like I said, any generic matrix A is not going to work. Like inverse A, you can't just take each element and do the inverse inside. Okay, so why don't you pause the video, all right? See if you could do this exercise. Well, yeah, pause the video, then I'll go show you the result now. So this one is not a surprise. This one, all these are pretty easy. The one that I should probably go over is this one. Well, this one, the first step is to take the transpose of this term here. If you take the transpose, so what you do is you flip them. So V transpose becomes V, sigma becomes sigma, and U inverse transpose. So that's what happens after you take the transpose. Now, here we mentioned U and V are orthonormal bases, okay? And that sigma is actually, I said it here, sigma is a diagonal matrix, okay? So if sigma is a diagonal matrix, then the diagonal matrix transpose is just itself, right? Therefore, I can get rid of this. And the transpose of inverse is just equal to the inverse of the transpose. So I can flip that. Now I can apply the inverse property. So the inverse, once again, I have to flip all of them. So it becomes U transpose inverse. And you take inverse again, they cancel each other out. Therefore, just U transpose. And then it's sigma inverse. And then it's V inverse. Now, since V and U are orthonormal, the inverse is equivalent to its transpose. And then that's how I end up getting this expression. Now we're ready to move on. Okay, so now that we've gone through some very basic manipulation and properties, this will help us later on. In the last class, we learn how to break down matrix via eigendecomposition. Okay, so the eigendecomposition, right? Eigendecomposition is such that you have a matrix, and when the matrix is symmetric, you are able to break it down so that these three matrix multiply together reconstructs A. And what is V? Each columns of V is the eigenvector. And what is sigma? Well, sigma is a diagonal matrix where the diagonal consists of the eigenvalues. Well, knowing the eigenvalues makes life easier in so many ways. Okay. So just because we have this diagonal matrix, I'm going to show you in a bit that we can make inverse of this easy, power of this easy, right? And and a lot of theoretical things suddenly can be manipulated because of this. So let's first talk about inverse. How does eigendecomposition make inverse easier? Well, let's say that A is equal to this, right? It's really easy to find if you have the eigendecomposition. It's easy to find A inverse. In fact, A inverse is just you take the sigma, right? You take the sigma and take the inverse of that. So this and we know finding the inverse of a diagonal matrix is really easy. Therefore, if we know the eigendecomposition, we basically also know the inverse. Now you might be asking, like, really, like, is this really, really true that you just take the inverse? Well, we can easily multiply them out and then you'll just see it. So if you take A, right, and then I'm claiming that this right here is the A inverse. And if this is true, this implies that this expression should yield an identity matrix. So let's see if it's true or not. Well, so here we're going to multiply them together, right? And it's supposed to be identity. Now, the first thing you notice is that I'm going to multiply V transpose V. Now, V is orthonormal. Therefore, orthonormal matrix multiplied by itself, like transpose, is just identity. So over here is identity. Now, identity is just one, so we can kind of cancel that one out. And after that, notice how you have sigma times sigma inverse. Well, that's also identity, right? Therefore, this gets canceled out. And now all we have left is VV transpose. And since V transpose, well, V is the orthonormal matrix. You multiply by its transpose. Once again, you got an identity, right? So this is basically showing you that if you have the eigendecomposition, it's finding the inverse is actually really easy. You just take the sigma matrix and invert all the diagonal. Finding power is also easy. Let's say we have some matrix A, and with this matrix A, what if we want to find a power to 3? Or if we want to find a power to 10,000. So I obviously you don't want to multiply A by A by A 10,000 times to get the result. That would be quite annoying and difficult. Now, eigenvalues give us a theoretical way to essentially identify them. And I'll show you how. So over here, right, let's just look at the case where it's A square, right? A multiplied by itself twice. So it's essentially this multiplied by itself. Again, we can use the exact same properties. Notice that it's just V transpose V, which is identity. So we can get rid of this. And now it's sigma. Well, sigma, this is sigma square. Guess what? Sigma is a diagonal matrix. Therefore, taking the square is really, really easy. All right. Therefore, if we want to take the square of this diagonal, right, it's just as easy as taking the square of all the diagonal elements. From this, we can conclude that diagonal matrices, right, are really easy to find the power. And in general, a to the any power, nth power, is simply the eigenvectors, right? and then you take the eigenvalue matrix and take it to the nth power, and that's it. This right here is how you find powers. So for example, if you have a vector v and you have some kind of matrix that manipulates v, and every time you multiply v by a, it like moves v by a bit. But maybe you want to do it 1,000 times and see what happens. So instead of multiplying v by a 1,000 times, it makes more sense to just perform eigendecomposition and then identify the ultimate matrix. Now, eigendecomposition also makes life easier with solving linear systems. So previously, we had this thing called augmented matrix, right? A, Y. We have the augmented matrix, and we can solve it with linear Gaussian elimination. But then later on, we found another way that x is equal to a inverse y. And then we found out that, what did we find? I forgot. But in any case, I think there was another way to solve for a. But if you know the eigendecomposition, we can yet solve a linear system another way. Let me show you how. So if we have a, right? So this is our linear system we're trying to solve. And we can do the decomposition here. If we do the decomposition, finding the inverse, right? Then we multiply inverse on both sides. Well, this cancels out. Therefore, a is simply v times this right here. And this is to find the inverse. All you need to do is essentially take the inverse of the diagonal. So this is essentially a inverse times y. It's just that a inverse is very easy to find once you have the eigendecomposition, or eigendecomposition. So we've really talked about why eigendecomposition makes life easier in so many ways. But let's look at it more theoretical. Like, we have this v, which we know is the eigenvectors, and we know sigma. But what really is sigma more than just this? Right? It seems to me they're very special, and therefore they could be almost a lot of things we haven't realized yet. Well, let's look at this question. What makes eigenvalue so special? Well, if we do a decomposition, I just showed you previously, right? You can run a decomposition. Ax equals to y is equal to ax equals to y. Okay? So now, since v is orthonormal, right? Therefore, if we multiply both sides by v transpose, so multiply v transpose here, then we end up with the expression where you have y times v transpose and v transpose x. Since v is orthonormal, right? Remember what I told you about orthonormal bases. Well, they act as a projection matrix, which you are projecting onto the new bases. So what's happening here is if you were to project y onto the basis of v, and then you project x onto the basis, and I'm going to call this as x hat, I'm going to call this y, then we got this expression. Now remember, sigma is a diagonal matrix. What this expression is telling you is that sigma, which is the eigenvalue matrix, is the reduced row echelon form. This gives you this sigma is the reduced row echelon form after you've projected onto a new basis. Right? So if you have this as a basis, now you do a new basis. After you've projected data on the new basis, the eigenvalues are the basically the REF form. Okay, so yeah, eigenvalues and eigenvectors are really, really special. Now, we talked about when a matrix is symmetric, which is like this. You flip it and it's still the same thing. The issue with eigendecomposition, the biggest one, is that a symmetric matrix is necessary. You have to have a symmetric matrix, or else you can't do a decomposition. Like over here, we essentially showed you that if we can do a decomposition, it makes life so much easier in so many ways, right? And there's so many special theories that can go into helping you to solve your problem. But it has to be symmetric, which implies that tall matrices doesn't work, right? Because this is not symmetric. Fat matrices doesn't work because it's not symmetric. And non-symmetric square matrices are obviously not symmetric, right? So how do we get around this problem? Well, I previously told you one way to get around is to multiply A transpose. Well, today we're going to more formally talk about this strategy, which is called the singular value decomposition. So, with singular value decomposition, essentially we're multiplying the matrix A by its transpose. Okay, so the idea of singular decomposition is that while matrix A may not be a square, right, or symmetric, but A transpose A and AA transpose are both square and symmetric. So take a look. Here's A. It's not square and it's not symmetric. But if you were to multiply by A transpose, notice the result is symmetric, square, right? So that the transpose is just itself. Alternatively, here's A transpose A. Let's try AA transpose. Notice how this is also square and symmetric. Right? Now, once we have this, we can now perform eigendecomposition on both of them. Okay? So the obvious question is, how does knowing the eigendecomposition of this and this really help us with A? Okay? So let's look at the math more carefully. Let's start with this. We know that we can perform eigendecomposition once we have perform A transpose A. Okay, so we can do eigendecomposition on this. And since sigma is a diagonal matrix, we can easily split it into square root of 2. So it's square root 2, square root 2. Okay, so this expression becomes this expression here. Now, square root of 2, like for example here, you can split it into 2, right? This times this, right? So in between the two sigmas, we can now put an identity matrix. So over here, it doesn't matter if we multiply by 1. So let's just put a 1 here. Once we put a 1 here, now remember, right, we have, these are orthonormal. We can put a different orthonormal such that it multiply to equal to 1. So this multiply will equal to 1, assuming that U is orthonormal. Therefore, A transpose A is equivalent to this giant thing, now that we split them. Now this giant thing, notice that this right here, if you take the transpose of this, it's just equal to this. Okay? Right here. This is actually A. All right. If you take, no, hold on a second. This right here is the transpose of this. And this is equal to A transpose A. All right. Therefore, this part, which is the transpose of this part, must be A transpose. And this part must be A. Therefore, we know now that A can be decomposed into two set of orthonormal bases. One set called V, another set called U, and the eigenvalues of AA transpose. So if we know the eigenvalues, we know the eigenvalues for sigma to the 1/2 as well, right? Therefore, it doesn't matter what shape of A is. A doesn't have to be symmetric. It can always get decomposed into these three matrices. Now, if A happens to be symmetric, then U will equal to V. And you're going to end up with V sigma 1/2 V squared, where sigma is just going to be the same. So actually, this will still be 1/2. Okay? So the goal now is, now that I've convinced you that A could be decomposed into three matrices, regardless the fact that it's not symmetric, right? The key is how do we then go about finding U and V, okay? So singular value decomposition is essentially all about finding U and V. Now, they're called singular value, SVD. These numbers are no longer eigenvalues. They are now singular values. For symmetric matrix, they're going to be eigenvalues. For non-symmetric, they're singular. And these vectors, instead of eigenvectors, we have singular vectors. So singular, singular. So how do we go about finding singular values and singular vectors? Okay, how do we find U and V? That's the next step. Well, it's pretty clear that if you multiply by this, we know how to find V and sigma. All right, we know how to find V and sigma. This is just eigendecomposition. Okay, so we can find V and sigma easily. So what we really want to know is how do we find U? So, well, if we do A transpose A, we can find V. Notice if we do A transpose, multiply the other way, right? If we multiply the other way, A transpose, well, if we take the transpose of this, notice this results in V times V transpose. So V times V transpose. And that's just identity. And then identity goes away. Now sigma square times sigma square is just sigma. And what we end up is U sigma U. So if we solve the eigendecomposition for A transpose A, we're going to get the V. But if we solve it A transpose, then we're going to get the U. And that's it. Like, you have to do it twice. It's a pain. But the general idea is pretty easy. And from this, we conclude that we can get both U sigma and V from eigendecomposition of A transpose A and A transpose. Okay? This is how we can get it. And once we get V, U, and sigma, this allows us to put everything together to get this decomposition. I don't think I need to cover that slide. Okay, so over here is an example. Over here is an example. So I'm not going to go over the whole thing, but you can see here the first step is to make it square. So right here, you multiply out, you got a 3 by 3 matrix, and then you multiply A transpose. So first you do A transpose A, then you do A transpose. Now you have two matrices, and now what you want to do is find the eigendecomposition for both of them. And if we start with the big one, right, here's the big one. We basically obtain the characteristic polynomial, which is right here. The characteristic polynomial solution give us the roots. The root is there for the solution to sigma. Once you have sigma, you go through a lot of process to basically find the eigen vectors. Now, I think we found how many sigma? We found 3. So it's 25, 9, and 0. So those are the 3 sigmas. So for 25, we got it. For 9, we also can get it, eigenvector. And then for 0, we can also get the eigenvector. Now, this takes a long time. And this, therefore, you know, it's it's very time consuming. In any case, by the time you get all three, right, every single eigenvalue is associated with the eigenvector. This one is associated with this one is associated with this one. Now, remember I told you the singular values tells you the contribution of each orthonormal basis. Therefore, you can see this one has a large contribution. This one has a pretty large contribution, but this one has no contribution. So it's not really contributing to the space because the eigenvalue is 0. Now, so basically, SVD, singular value decomposition, is just eigen decomposition doing it twice. Right? You have to do it twice. One time for A transpose, another one for A transpose A. Now, this is a pain. All right, SVD is used quite a bit in machine learning. We actually, in machine learning, work very hard to make the matrix symmetric. So we deal with eigen decomposition. But there are definitely times that it's not symmetric. In any case, if you don't learn SVD now, and if you're going to do a master or PhD, you will run into it again. So you might as well learn it the first time. Now, SVD is the single concept that actually encapsulates majority of the linear algebra class. So if you just take a second and really think about everything we've done so far, I hope every one of these topics you would be able to like know how to deal with it, like various matrix operations. I hope by now you know how to do addition, subtraction, division, and inverse, right? Column spaces, null space, eigen decomposition. So obviously you need eigen decomposition to do singular value decomposition. You need to know how to make unit norms. You need to understand the concept of norms in order for you to make unit norms. You need to know Gaussian elimination. You need to know span of spaces, linear independence, norms, orthogonality, orthonormal normality, vector spaces, whether a matrix is square, fat, tall matrix, eigenvalues, eigenvectors, you need to know that. Normalization of the vectors, orthonormal matrices, and projection matrices. So, like you would need to know every concept here, every single concept, in order for you to really understand singular value decomposition. And therefore, it's like just a really good way if you do a couple singular value decomposition and really look into each step and see all the assumptions underneath, you will realize by now you've learned a lot this semester. So, as a summary for singular value decomposition, SVD allows you to take any non-symmetric matrix and decompose it into 3. Now, U is an orthonormal basis, so is V, right? And these are the singular values. To perform SVD, you need to perform eigen decomposition essentially twice. One time A transpose A, another time A transpose. And each time it will give you either the V or the U. Now, solving a third order or higher polynomial is very painful. Very painful. If you try to solve this, like, I don't know, it could just take you a long time. So ideally, like on the exam, I'm gonna try very hard not to give you this problem. I will do what I can to make it much easier to factor, but you would need to know how to factor. And this is where you knowing Python would really help you guys in the future. So you don't have to do it by hand. And the way you would do it, SVD is as easy as a command, SVD. And then after you do the SVD, voila, here's the U matrix, here's the sigma, and here's the V transpose. Now, if I were to multiply U dot sigma, now sigma and then dot V. If I were to do that, notice I would recombine it together. So this is the sigma matrix, by the way, where the diagonal are the eigenvalues. Okay, so singular value decomposition, and over here it shows you how to do the reconstruction. Next, well, in real life, if you end up with like characteristic polynomials and you need to find a root, like this one, right? Like it could be a real pain for you to like deal with these things. Now, with Python, specifically SymPy, it allows you to solve it. So let's say we have an expression where it's lambda to the cube, 7 lambda square minus 10 lambda square, 3 lambda minus lambda. Okay, so one thing you can call is to just simplify. How do you simplify this expression? Well, after you simplifies it, it's lambda times lambda square minus 2 lambda plus 2. So you can simplify expressions directly. You could also factor. When you factor out, you can see very quickly what the root of the polynomial is. So you can see lambda eigenvalue is just 0, 2, and 1. Right? Or you can have it solve an expression. So over here is trying to solve an expression where lambda is what you're trying to solve. And it gives you the root. So the root is 0, 1, 2. As you can see, 0, 1, 2. Okay, so you can either just factor out the polynomial or it will just tell you the root directly. And other times, if you have like these multiplication and you want to expand them back out, then over here, this will allow you to expand it. So knowing how to do this, all right, whenever you encounter polynomials, will just make your life so much easier. For the final practice, here is a non-symmetric matrix, and I would like you to essentially see if you can do it. Divide them into U, sigma, V. The answers here, you can double check your answer later. Okay? So that is the lecture for the day. I will see you next time.